I can't hear him. Okay. So
Extra large.
here we go. Don't worry about Whataburger shirts. All right. So we're talking about the electromagnetic spectrum. Sorry, I had some technical issues and didn't get the video started. But this is the stuff that we can see. Everything else was part of the electromagnetic spectrum, and this is how we look out into space, particularly with X-rays and with ultraviolet radiation. We do get some infrared, and radio waves are part of like the cosmic background of radio waves. We can look at all of this, but in general, we really use ultraviolet radiation and X-rays to kind of look out and see what's going on in the universe. In fact, one of the newest telescopes, the James Webb Telescope, is looking around here in this part of the spectrum, so we can see more and more stuff that's out there that isn't necessarily visible through a standard telescope. So let's see what they say up here. Electromagnetic radiation consists of photons. The spectrum includes all wavelengths, even the ones that we can't see. And we did this in chemistry. We did a little bit of work with frequency and wavelength. So remember that frequency and wavelength are inverse. So I believe it's this. The speed of light is equal to your frequency times your wavelength. And this is lambda. It's an upside down Y. This is your wavelength. The fancy F is for frequency. And so you just rearrange this to solve for frequency or wavelength when you know one and not the other. The speed of light always stays the same. It's a constant. It's 3.00 times 10 to the 8th meters per second. And so wavelength is literally going to be a length. That's going to be your meters. Frequency is like a cycle. How frequent does something happen? That's going to be a number of times per second. And so that's your cycles. And that's how you get to the speed of light in a way. And it doesn't matter what your frequency or wavelength is. The speed of light is always going to be the speed of light. It doesn't go slower. It doesn't go faster. It goes the speed of light for the most part. When you get into an atmosphere, it probably slows down just a little bit. But if your frequency goes up, your wavelength has to go down. If your wavelength goes up, your frequency has to go down. And so we covered this in chemistry quite a bit. I know y'all remember me doing this thing. Frequency goes up, wavelength goes down.
Oh, I remember that.
Yeah. So the electromagnetic spectrum, I've already talked about that. Radio waves, microwaves, and infrared. So if we come back up here, radio waves, microwaves, and infrared, these are the things that are longer wavelength and they're lower energy. So we all have microwaves in our house, right? When you're heating up your Hot Pocket, are you afraid to go and like hold your hand on the handle for the last 2 seconds because you just can't wait? You got to open the door as soon as the buzzer goes off. Yeah, you're not worried about that. You take that microwaved food out and you eat it immediately and probably burn your tongue a little bit. These aren't really necessarily dangerous. What do we use infrared for?
Guns.
Well, kind of, but more specifically, what do you use with the guns?
The light to see in the dark.
Yes, to see in the dark. So infrared goggles help you see in the dark. So we literally take goggles and concentrate the infrared and put them directly into our eyes. We're not worried about that. And then radio waves, literally right now, we're all just bathing in radio waves. There's like 20 different radio channels in the DFW Metroplex. And if you had a good radio, you could pick them all up in here. And it's just all bouncing around the room, hitting our body and bouncing through our body all the time. It's just radio waves. So these are low energy. They don't really harm us. They are there and they move around all the time. And there are things that naturally create these out in space that we can look at. And so that's why they have these three kind of grouped down here. Radio waves, microwaves, and infrared. This is the low end of the spectrum. Waves of infrared are a little bit shorter. They're just outside of our visible range. So right next to infrared, you see the visible range of light that we can normally see. And so we use infrared to look at different galaxies and other things that have that infrared spectrum that they're giving off. Almost like a heat spectrum, but a little bit different. So we come down a little bit further. They talk about visible light, which is just a small section of what we can, well, it's all we can see, but it's a small section of the electromagnetic spectrum. You can use a tool. I meant to say the word prism, but I read the word tool. You can use a prism to separate that out. So if you have white light, white is not on that visible spectrum. There is no white in Roy G. Biv. So in order to get white, you have to kind of contain all of these together, which is why if you take white light or sunlight and you pass it through a prism, you get the nice rainbow, the red, the orange, yellow, green, blue, violet. And so that's kind of what we're looking at here. And we can take white light that comes from stars or whatever kind of tint it is, and we can separate it out and look and see exactly all the different spectrums, which is what they did in the news story. They took that spectrum, listen, look, hey, they took that spectrum and they noticed there was a dip in part of the spectrum. And something had absorbed that wavelength of light before it left Venus, and when it got to us, it just wasn't there. And the only thing that we know that right now that can absorb that specific wavelength of light is phosphine, which, as we know so far, can only be produced by microbes or by artificial complexes. What are you doing over there? All right. I know I've been talking for a little while. Come down here, past visible light. Here's your visible light spectrum. And then we get to the high energy stuff. Ultraviolet light. What is UV light good or bad for you? Bad. We use sunscreen. We use sunglasses to protect us from UV light. You get a little UV light. It's not going to like kill you immediately, but over like 60, 80 years, it could make you more likely to have skin cancer or eye damage. There's all sorts of things that can happen. So we try to protect ourselves from UV light. Now you go a little bit more powerful, and X-rays, will those hurt you?
Yeah.
Yes. When you go to the doctor and they give you X-rays, they put like the lead vest over your chest and your vital organs, and then what do? They step outside the room and press the button. But they're like, you just stay in here with the X-rays. We're going to go out there.
They put it next to my face.
Yeah, at the dentist, they literally blast you right in the face with it. But one of the things is, if you get a couple X-rays like once a year, it's not really enough to hurt you. If you're the doctor and you're in the room with X-rays all day, every day, that's not going to be good, which is why the doctor leaves the room and they blast you in the face with X-rays.
This is why I have to
Yeah, literally like at the dentist, like right up in your face when we blast you. And then gamma rays are really bad. Gamma rays, in real life, you've been exposed to radiation from like a nuclear power facility, and you're going to have severe problems. In comic books, gamma rays create the Hulk. You will not be the Hulk. You will probably just die a very painful death. But these are the higher energy things than regular visible light. This is the stuff that will more than likely hurt you. And we do look for this stuff too. So they talk about the wavelength of this. Hey, pay attention and listen. Where's my thing right here? All right. They talk about the wavelengths of those parts of light. And let's go to the next page and see what they got to say. Come on. There we go. So there's 2 pages on this one. Remember that. And they talk about our different tools. First off, optical telescopes. Optical telescopes use lenses and mirrors, and they're basically looking for the type of EM radiation that we can see visible light. Optical, like your eyeballs. That's what we're looking for there. And so they use lenses to make things better. This is your standard telescope. We also have reflecting telescopes. This one's called refracting because it bends the light into a point and kind of focuses it. We also have reflecting telescopes. These are like the big barrel telescopes. If you've ever seen someone with a nice telescope, it's got a mirror at the end. The mirror points all the light to another mirror, and then it goes into the eyepiece, and you can kind of view it pretty nice through that. Yes?
Speaking of telescopes, how much do you think those big ones cost? Like the Alma one?
Like what? Oh, the one from the news story?
Yeah.
Oh, those are like hundreds of millions of dollars. The government has to build those. If you want a nice telescope like this, that's maybe like that big around, you're talking like $300-400 to a couple $1,000. It depends on what you have. because there's ones that you have to position yourself. But the new thing now is motors and GPS units, and you can basically like type in "I want to see Venus," and it'll point to the part of the sky where you can see Venus.
If you
Well,
have-
it's hard to find the thing that you want to look for in the
if you
sky.
have hundreds of millions of dollars, could you build one of those big ones?
Yeah, as a personal, like as a billionaire. Oh yeah. More than likely, you would just donate to a scientific organization because you probably got your billions off of business, and you don't know anything about a telescope, so you'd have to hire some people that do. But yeah, you could just donate the money and get your name on it, and it could be like the William Bailey "I'm a Billionaire" telescope. That's
look at it, look through it and stuff.
oh yeah, you probably would. Yeah, if you donated money for sure. Yeah. Or they just throw you a big party. I don't know. Who knows what rich people actually want. So like the Hubble Space Telescope, everybody's kind of heard of the Hubble Space Telescope. That is one of the ones with a mirror. It reflects the light. In fact, one of the big things is they sent it up into space. Somebody had done one of the mirrors wrong. Couldn't see anything at the beginning. It's just all blurry. It was really broken. They had to send a space shuttle up. The astronauts had to fix it in space. And then everything was good, and it's been lasting for a really long time. But you got to get the mirrors just right to be able to do it.
How big are the mirrors in that, do you think?
The Hubble Space Telescope, I'll look it up in a second. Well, let's see. Do they say?
How strong are they?
They don't say here. I'll look it up in just a second. You're probably talking maybe 9 meters or something, because it's got to be able to fit on the rocket. They're not that big.
9
9
meters.
meters?
Yeah, well, it's big, but it's not like a huge satellite kind of thing big.
That's like half this room.
Then maybe I'm wrong.
That's more than half this
Well,
room.
we'll look and see. Hey, we'll look and see in just a minute.
You showed us last year, I think. Go like the size of that. The whiteboard.
Maybe. Well, I bet it's a little bigger. I'll look and see in a second.
That big.
So the next type is non-optical telescopes. These are things that don't look for visible light. They look for things like your radio waves, infrared, microwaves, all these kind of telescopes, X-rays. You can pick up a lot of stuff that you can't see visibly on the electromagnetic spectrum. Like one of the things about radio waves, they penetrate stuff pretty easily. Does your house block out a radio wave? No. So it's kind of difficult to build a satellite dish that will reflect your radio waves back to a single point where you can read them all. So it's a lot of material science to make sure that you're picking up all the radio waves and you're making sure that you can see all of them. So now we're down to the bottom. So I will let y'all go ahead and open up the assignment. It's just those 2 questions. Let's see what they ask about. The electromagnetic spectrum includes all wavelengths. You can go ahead and open them up. All wavelengths of electromagnetic radiation, including visible light. Define electromagnetic radiation. You should be able to find that in the reading. Explain why there are different colors of visible light. So each different color is just a different wavelength. Those are the different colors. So red is a specific wavelength. Yellow is a different one. And they have that back on the first page. Once it switches over. Come on. Come on, son. Am I there? Yes. So if you come down here to the visible part, they kind of show you blue is like in the 400 range, green is the 500, yellow, orange is 600, and red is 700. Those are your different colors for your wavelengths. What else does it ask? Identify 4 kinds of electromagnetic radiation other than visible light. So you just go to that first one, the first chart on that page up at the top. Oh, that wasn't it. Over here. Go up to the top and give me 4 of these different types of electromagnetic light here. And what else did they want? Put them in order from longest wavelength to shortest wavelength. So long wavelength down here, short wavelength up here. Yes. Yeah, make it quick because you got to get the assignment done. Yes. Did you already do the assignment? All right. Let's see.
The first one.
Astronomers use a variety of technologies to sense electromagnetic radiation. Identify the two main types of telescope for magnifying visible light. So that's your refracting. It's probably around the corner. Refracting, which has the clear lenses, and then reflecting, which has the mirrors. Describe how each kind works and identify advantage to one over the other. Provide two reasons why astronomers place telescopes in orbit around Earth. I didn't really cover that, but basically one of them is our atmosphere causes a lot of interference with different parts of the electromagnetic spectrum. We want to be able to see everything, and some stuff isn't going to make it through the clouds, some stuff is going to make it through the atmosphere. Another reason could be if you have it here on Earth, half the time, depending on what you're looking at, you might not be able to see anything. If the sun is up and you're trying to see other light, can you really see the stars in the sky when the sun's up? No, they're still there. You just can't see them. So if you put it out in space, you can always have your satellite pointed away from the sun, and you can always see stuff 24 hours a day instead of having to worry about the sun. So they probably have a couple other explanations here if you want to look through the reading. But yes, that's going to be your assignment for today. If you have any questions at home, please send me an email and go get a Hawaiian shirt and put it on at home so you can participate in Tropical Day. We've got all sorts of people here in class with their tropical stuff on. So have a little fun and take a vacation at home. Have a nice day. Send me an email, and I'll talk to y'all tomorrow.